Okay, today I will introduce a paper named A Global Geochemical Database Structure for Rocks. And the first author is Leonard. This paper is published in Geochemistry, Geophysics, Geosystem in 2000. And the speaker will give the presentation in Wednesday is Dr. Martha. And she got a PhD degree in the University of Cambridge in 2018. And after that, she worked in Australia for several years, and now she's the research assistant in the university in Germany. And also, she is the coordinator of DIGIS, which working for the infrastructure of the database Drock. And following the development of the earth science, the amount of the geochemical data is growing exponentially. Like when we do a research about our data science, we will need over thousands data or even more data. And the rise of the interdisciplinary science means that the scientists need to access all kinds of data, and the data must be evaluated for the completeness and the reliability. And the geochemical data themselves rapidly become updated. If they didn't have the necessary metadata to describe the data kinds like which samples types, rocks or minerals, and other information. So what we need is a database that contains all the geochemical and petrological data and its supporting metadata. And also the database must be in a form in which it can be accessed by the scientific community, which makes more useful for our research. And the author create a kind of relational database structure for this situation. The object is for chemical and petrological data of all types of rock samples with essential metadata. And it has applied in two kinds of database, named Rich Path database and Georock. And the data types in this kind of database have two kinds of data. The first one is about analytic values for the rock samples, like the major oxide and trace element composition, and so on. And the second part is the metadata, which describe the samples. It has three kinds of metadata. The first one is analytic metadata. It includes the analytic methods and the sample materials. And the second kind is sample metadata. It includes the description and provenance of the rock samples. And the third part is the reference metadata. It includes the bibliogeographical information for the reference, like which journal published this kind of data and who wrote the papers. And the model of this kind of database, like the picture shows, the data are stored and presented in the form of the tables, like the three kind of tables. And the tables consist of fields and records. The fields means the vertical columns, like the year from fields in the table expedition. And the record means an arrow, like the expert to the arrow. And each table has a unique name, like the expedition, the shelf scientists, they are the unique name. And each table must have its primary keys to make every arrow can be unique identified, like the expert column in the expedition table is the primary key of this table. And each table and record in a table can be uniquely identified. It means in every table, the column's name is unique, and the various tables are related to one another through the foreigner keys, like the Like the table shelf scientist, the expert and the person are the foreigner keys from other tables. And we could, through the foreigner keys, search the information into the three tables. And the primary keys have to be unique, but the foreign keys are not. For example, in the table shelf scientist, in the clone expert, the value is not unique. It has the value 2 is repeat 2 times. And the table 1 in this paper, it describes the archives of the table in this kind of database. The author lists over 30 kinds of tables, so I only carved part of them into the PowerPoint. Like the table chemistry, it lists the compositional values with the standard deviation and uniques. And the table data quality, it describes the data quality of the analysis, like which method it will use and the procedure that the method. And the table 2 in the paper describe all types of the fields contents into each tables. Like the analysis num is the primary key of the table analysis, and the bench num is the primary keys of its table. And this part is about the sample related tables. From the figure, we could see the table samples is the unit of this whole part. And it also has other tables like the sample age and Drock mode and expedition that describe all the information about the samples. And from the table 3 in the paper, it describes some items choice of the table. Like the clone location type, it could have the 3 kinds of choice that we could fill in the table, like the ocean, the island group, and so on. And this picture shows the analysis related tables, like the table chemistry. It contains the chemistry values of the samples, like the trace element and oxide compositions. And the inclusion tables includes the mineral types and the heating temperature of the inclusions. And this figure shows the reference related tables, like the table person, table institution, to describe the author of the paper. And it also has the problems of the unique sample identification. The first problem is that sample names from publications are often not unique. Like the paper 1 will have a sample name D1, and the second paper will also have a sample name D1. For example, the name of the sub-area samples from original publication is usually entered as the sample ID. So it will make the sample ID in the database are not unique. So we couldn't make the connection, the corresponding relationship between so many tables. And the second problem is only if the pertinent information is accessible, that all samples can have the unique sample ID. Like, but for example, names of sub-areal samples are not systemized, and the metadata are usually lacking. Like in the paper, it's usually lacking the age or the location of the samples, so the unique sample ID cannot be created. And this figure shows the organization progress of the database. Like in the table in reference, they have 3 samples named the sample D11. It has its bench num in the table batch. The num is 100, and we could use the bench num to search the information in the table analysis, because the bench is the foreign keys of the table analysis, and we also can use the analysis num to search the related chemistry information from the another table. So, and we need to focus on one special things which is different from our routine table, is that she makes the trace elements into the item measures, not in the columns. It means like if one sample only tests 2 kinds of trace elements, that means we only need to store 2 rows data in the tables. It will save many empty cells because we usually make every trace element into itself columns. And this kind of organization, we have 2 main advantages. The first one is making the items variable. It will make the if we want to change the values of the chemistry or analysis value, it will make it easier. And the data storage is more efficient because we avoid many empty cells. And this part is about the operational aspects of the database. The physical structure of the database needs to be created with a relational database management system, like the Oracle or SQL Server and other software. And in this progress, we need to make sure the uniqueness of the primary keys and the data integrity and correct referencing of the primary keys by foreign keys. And the access to the database for searching or other functions is best provided over the internet. It will make it more efficient to search the data. And it has 5 general characteristics of this kind of database. The first one is comprehensiveness, because this kind of database contains any type of analytic data for rock samples. And the second one is that it makes all kinds of data accessible because it has established the corresponding relationships in the database. So we only need to know one information, like the sample ID, that we could use the sample ID to search other informations. And also it makes the minimal redundancy because it avoids unnecessary repetition. And it also has the efficient storage because the minimal redundancy. And this kind of database is very flexible because it allows the board because we could change the values only in one individual tables, but in our routine ways, if we want to change our data of one samples, we need to open many kinds of tables to change it. It allows the broader application of this kind of database. And I also searched some other information from other authors' papers. the more function of the Georock, they have add a Google Maps-based search, which allows users to query by geographical location. And they also add a discussion forum that the users can chat in it. And it also allows users to mark typographical errors. And also the Georock database have joined the EarthCam consortium with the database PathDB and NAVDAT. So we could search the information from these three kinds database in the EarthCam website. And the concepts for Georock 2 edition, they want to make an open access to end-to-end tests and data mining. And they want to make a data DOIs like the paper have its unique DOIs. They want to make every data has their unique ID. And they want to link to our geochemical sample storage system and also make a multi-way to harvest their data and also content to other database. And in the paper of Chamberlain in 2021, she figured out some problems of the data culture in geochemistry. The first problem is that there isn't a globally standard of data, and the solution is nowadays more communities at national and global levels are emerging to advance, integrate, and share geochemical data standard and promote best practice. And the second problem is that data publishing and metadata requirements are variable between different founders and journals. But since 2013, minimum metadata requirements for publishing geochemical data has been defined. So maybe in the future, we will use the same standard to publish the data. And she also figured out the future of data culture in geochemistry. All the data should be shared via repository that follow the FAIR principles. These principles means findability, accessibility, interoperability, and reuse. And every data set should be assigned a globally unique identifier, such the DOI of a paper. And every physical sample should have an IGSN, like the unique sample number. And that's all.
Okay, thank you, Luyan, for leading through this. So, yeah, does people have any questions or comments so far? Yeah, it's an interesting work that I've been doing. So we are also working with Geochemistry, with the speaker Martha. Because one thing that actually in this part they didn't talk about the cons of their database. I think that it's pretty good. It's really good work they've done. But the problem with this database is that there are many errors in their database because the data source is the data source, I mean, the publications, but the data located in this database, Drock, do not reflect the exact numbers into that locations of the original publication. And for give example, if someone published a olivine composition with MgO with certain number, maybe 40%, then you have the silicon dioxide concentration of 35%, and then you have the aluminum oxide concentration like 0.2%. Now that's what you reported, but in this database you may get silicon dioxide concentration with 0.2% because just shift every row of data. So actually, Luyan, so in this work that did they mention about that? How did they extract data from the publication?
No, they didn't describe this part. They just described the structure of the database.
Okay. So for the algorithms using the identification to extract numbers in this different publication PDFs are not smart enough nowadays because the scientific symbol is complex and the people do not have a uniform way of standard way of publishing their tables in geochemistry. So that's the origin of the problems that the database has, and that's why they're working with us, because we have the ability to dramatically improve their quality. So Wumi mentioned about that there should be more awareness for people. If people want to similar formatting is used. Actually, the claim has been made by community for a while. Like the Chapman's paper was published in 2014. There's another publication talking about geochemistry. The idea or the publishing standards people have already talked about it for a decade, but not much progress being made on that end, because to me that it doesn't really create an incentive for researchers to publish a paper in this way. So we need to give some rewards for people for doing that. But in the short term, I think it's very hard. And the other end for it is that for the database or the publishers, if they could set the requirement, asking people to publish in this standardized way, or directly publish their data to the database of Drock, for example, then that will be much better. But the problem is that the publishers like Elsevier or Springer doesn't have this strong incentive in doing so. So currently, I see what we are doing at the third path, a third way, is that people collect this data and clean them, and then use the clean data to do more research, and then people publish them and publish the research together with their clean data sets. So that's exactly what we are doing. Not only we do this, but we also look at other people who are doing similar things like us. Then we collect those sample numbers, and then we send this feedback to Drock, so that the quality of the database could improve. So that's the thing that actually why that they would work with us.
Yeah, maybe the data cleaning will be the advantage of our database.
Yeah, that's it. Yeah, Brian.
Yeah, how open source is Georock? Like, how accessible is it? Like, if I were to go to the internet and check out a database and then find an error, how would I then, let's say, leave a comment or perhaps upload a revision? And every revision, your revision history for each entry in the database says, okay, error was found, so now we're at version 2. So you can have versioning just like you do on GitHub. So like, I don't, what is that experience like in terms of interacting with Georock?
So it's just a beginning. I want to know more. So then maybe you could talk a little bit about your experience of uploading to Georock. And we're going to have a meeting with Georock on Wednesday. I don't know if it's convenient for Ben to open the mic.
It's
Yeah,
fine.
yeah,
And
but
this is something
yeah,
we
yeah,
can
yeah.
ask
So
later.
it's not in the current status like a GitHub. So because they are still the platform, so all the data needs to submit to their end, and then they have to upload it from their end. So for the users, you cannot just do it by yourself. But they do give a different tag for the clean values, which they nowadays they try to call the expert data sets. So they took those out, and then because the clean data, a lot of them were directly originally from Drock, so we have their unique ID or unique number or unique link. So we kept that. So then we correct them and then upload to them. So now I think I'm not clear that how Drock is going to do it in the end, because in the previous communication, their staff people were saying that they're trying to put another flag on it so that in the future, for other users to do it, they will see, okay, this is what Drock raw data looks like, and then this is a exactly same sample number. Then you have another data that is clean one, so it's uploaded from somewhere like us. So this is one way. Another way, they say they are going to directly correct it under their server infrastructure. But I don't know that. I think it's easier way now if they just put another tag into data. But I don't know that how exactly they are going to do it, because in the other way is that how do they know that their data is wrong so that they are going to correct it? I just see that there's one disadvantage nowadays they have is that the users, you cannot directly just go there with data sets and then clean it by yourself. You cannot do that. I think it's a little bit like Wikipedia. But the advantage is that you could edit it, but the problem is that you're going to change maybe some people, they're just going to make a little mess, and that is hard to clean it up.
Well, yeah, two comments on that. So like if you go and contribute to open source code, you always submit a pull request. Like you don't have write privileges. You submit a pull request to say, okay, here are the changes that I'm proposing to make. And then I will then ask the original authors or the person who maintains the database to review everything that I changed to have a consistency check. So that could be a manual check. And also two, you could have an automated check. Like if the standard format is, I mean, nowadays you can standardize a format pretty easily. So you can have a script that auto-generates an empty table, and then you populate it with your own data. And then there's an easy consistency check. Like you can always check, does this database have the exact fields that the standard says it should have? And are these attributes like the right data objects? Is the name a string? Is the analytical value a float or double precision? So everything, you can have those quick automated checks, like when you have a source code and you want to do like a build bot, like you say, does my every change I make, can my code still build correctly? So I think those things, I'm sure the Georock people are thinking about these things as well. But that would probably be the way. Like you can have 2 levels of checking. You have an automated test, say, okay, I make a modification to this table. Is everything still consistent? And then I have an expert check. Says, okay, I'm going to go look at the paper and look at those numbers. Okay, yeah, I think you're right. Let's go ahead and approve this. And now you have a new version tag.
Yeah, I think so. So Georock 1.0 was a couple of years ago. Now they want to update to the 2.0. So the speaker is going to speak on Wednesday, and she's going to tell some more details. I think it should be an improvement of what Brian has been talking about, that they should get the manual review, allowing the users to upload and then they just do that manual review apart. But I don't know how well they manage that. And so they claim they have quite a strong IT support team behind, but I don't know how strong it is and how many people are dealing with that. Maybe have 2 extremely smart people behind, but then that's all the people we have. Then probably it will be slow because you do need a lot of people to implement these ideas. So I don't know.
Yeah, there's always the problem of getting the ball rolling on something that causes that needs standardization. And I think that was Ormi's comment as well. Like if you want people to adopt it, the standardization has to be very easy to adopt and very common. So probably I could envision like a funded project is one where some group goes through and populates GeoRock with the standardized format, like a small dedicated team of maybe the last 10 years worth of papers, like all the hot topic databases so that people can easily get it. And then once they see how easy it is to get it, to access the data, to look at the raw data versus processed data, then you start to build some momentum for everyone else to just submit on their own the format. So it's hard for like a small team of 1 or 2 people to try to convince everyone to adopt a format, do a little workshop at AGU, hoping people show up. I think it has to have like a ton of data has to be there already, that it makes it attractive for other researchers to want to go in and contribute.
Yeah. So what I see, I think that's could be the way to go. But unfortunately, there's no funded projects like that in the world now, or do it very effectively. I think that's another problem, is that it might need a lot of money to do it very effectively. So that's the value, the thing that me and my students are working on now, is that basically we are doing that work, but under the name of some data-driven groups like us. We are not the only one in this plan doing this. There are a couple of other groups are also doing similar things, that they collect data, they clean them, and then people have a project, science project in their mind of certain science questions that they were trying to answer. Then by collecting and cleaning this data from GeoRock and different and more recent publications, like GeoRock, they haven't included any publications before after 2015. So this small group of people, they collect this data, clean them, and then they answer the science question, and then publish a paper, high quality publications, at least in the community, and then they publish all the data along with the research. And for hard rock, for example, for what they were interested in for the solid earth, so that the data, chemical data in different time scale. From my perspective, if we could reach 1 million or 500 million, then that is already very high time resolution for the geologic history, no matter whatever question people want to pursue. So actually, that's still within a reasonable amount of data that several groups of people, if they're really dedicated in doing so, that could be achieved. But they still need a lot of people in this several limited research groups to collect and clean this data and make it a reality. So once this could be done, I think this is it is going on, and it's on the way. And then this small group of people will make this data responding to GeoRock, and we are also making our own SQL for our purposes, because it's faster. We are faster than GeoRock to respond. So by this, since this is open source already, then for other researchers, whatever goal they want to achieve with this data, they could easily request, because it's open source. So what I see that, Brian, what you propose is I think that is a ideal way of doing so, but unfortunately, we don't have such large funding in the world now really dedicated to doing this, because if you really hire a lot of people full time in doing so without the science goals, it could be very expensive. And you also need a lot of experts in this field in doing so. So we would do it. So we do the other way around. So we spend some money and then try to create some science results, and along the way, make all the data open source.
Yeah, that sounds reasonable. Just any way to advertise your format, indirectly, like you said, through a publication would be good. And then also,
yeah, Yeah, I think for us in doing so, then for other researchers, if they're only interested in using, then it's fine. They're just going to use it. But if other researchers, they're going to say, okay, we're going to collaborating with us, and they're interested in similar projects in this way, then we would encourage people to publish in the similar format or standardized format. So from my perspective, rather than asking 1,000 researchers, geochemists in doing so, who just publish 1 or 2 publications a year and on a very limited amount of data, I prefer to just catch a very limited number of researchers who are really dedicated to data-driven one, because they basically collect everybody else published data in their standard ways, which in this case, I think as long as there are certain standards that people are doing for 10,000 samples, then it's easier we make a one geochemistry way, which is what the ultimate goal people want to have, is that all the geochemistry data should have a standardized way, not only into the hard rock, solid earth chemistry, but also to the sedimentary geochemistry, the groundwater hydrogeochemistry, the gas geochemistry, as well as organic geochemistry, because fundamentally their data format is the same.
Yeah, that makes sense. And I think like with every data format, there has to be easy tools available to interface with it, to write to it, to read from it. Like let's say with remote sensing data, GIS or Geodesy, there's GeoTIFF format, lots of NetCDF format. Those things have become so standardized that tools like GDAL, a library, super powerful tools were developed so that these things become super, super easy to read into. You get all your metadata with a standardized API. So with the data format comes the tools to read it. And so like whatever your interface is, like I think most SQL tables can be read, let's say by pandas in Python, and probably they can also be read in MATLAB as well. So as long as those standardized tools always work, I think it would be a lot, adoption of the format would be easier, is what I would think.
Yeah, I totally agree with you. So that's why we are writing a Python framework called the Geochemistry Py. So, but that one started with attracting people to say that, okay, geochemists, you don't have to learn the details of machine learning in Python, and then we're just going to do it for you, and then just going to choose whatever algorithm you want to choose, so that this is the way for you to process data. But the next steps that we're going to put the clean data sets from the Drock and other people's work and apply it together in this high quality SQL. And then we are going to request data for it. So basically reading through the pandas. So Sunny, could you share your screen if possible to show very briefly, Brian, of the Python framework? Maybe could give a very short detour of the product we already have. So Sunny.
Yeah, okay.
Okay. Take your time. Share screen. So Sunny is currently an undergraduate student in geophysics at the Sun Yat-sen University in Canton, and he got an offer from the National University of Singapore in computer sciences as a master program. So he's going to move to Singapore in the second half of this year. Yeah, so he is leading the Python framework, and we already have a product that is running, and we're still trying to improve it so that it will be more accessible to geochemists and probably, yeah. So.
Okay, I'll just show a demo on how to run the Python framework Geochemistry Py. And it will tell us what's the interface to run the open source software we are going to achieve, and it is on progress. Okay, this is the interface to start the Geochemistry Pi, and the users just need to choose the option showed in the interface here. And in the first version, we are going to launch in the command interface. Like we choose the provided testing data, and we insert 4 kinds of data set into this open source software. It aims for 4 kinds of the algorithm mode or the machine learning gram usually use. So I just use the provided testing data, and I will choose the data for regression, and I choose one. Okay, and here is the data sets processing, and here is the sample name, the second line, and this is the there are some major elements also. And I move forward, and I can just project a specific element into the word map, and if I choose 1 year, and just choose one kind of the major element, like the 10th element, like this one, and I choose 10, and it will save the figure or its drawers in a specific directory or we designate, and we move forward. And if I chose something wrong, it will tell, sorry, and I just continue to run the progress. And like here is the data selected part, because we just want to process a specific range of the data set. So I just choose maybe the 10th major element, and also from the 12 to 15. Like this one. Okay, and it will tell that the specific serial numbers of the columns has been chosen here, and move forward. And this is the brief information about the data columns we have chosen before, and just move forward, and it will tell some basic statistic information of the selected data sets. And we can just continue to add more function and provide the user more useful or statistic or technique to process the data. And the current framework just have like just try to cover the whole progress of the data mining jobs in the by using the machine learning algorithm. And we will provide some strategies to deal with the missing values. And like we choose medium, and then it will just fill up the missing value and provide some basic statistic information as well. And it will provide 2 ways to explore whether the imputing is good for the current data set also. And then we can do some feature engineering option, like I choose years, and we need to create a new feature, and which means that maybe we can do some basic operation by like add some element together, or by just subtract or element by another, and other combination of the simple operations. And I just give a new feature. Okay, just, and I can do something like I just use the A column to plus the parentheses B over C, and like minus by A and parentheses and multiply by D. Okay, and it will calculate the new feature column by doing the operations we inserted before and move forward. This is the new feature column we have created. And then here is the post-process data set. And we see that the new feature column has been appended to the original data set. It will be the sixth column. And here is the new feature we created based on the previous operation we do by the combination of some columns in the previous data set. And we move forward, and it will tell, do we need to make another new feature? And we choose no, and we exit feature engineering mode. And here is the option for the mode, like we can choose regression. And then because for the supervised learning algorithm, we need to divide the dataset into X, and we need to create a data column as the target column, so Y. And here we just to create X data set, and we just do it according to the input format here. And like I just choose the first column to the fifth one. Sorry. Okay. And we have successfully created the X data set, and we just need to choose the Y data set, and we just choose the last column, which is the new feature column we have created, 6, and then this is the Y column. So here is the part for selecting specific model, because the whole project is on progress. So currently for the regression mode, we provide 2 kinds of the algorithms, but after that, we will just append more algorithm as into the framework. And here we just choose the first one. And then because for the polynomial regression, we need to specify the maximal degree of the polynomial features, and we choose 2. And then it will just run all of the like the methods we just put we have put already in the framework, and it will like show the polynomial regression formula like here. And this is the simple demo of the framework we are currently working on. And this is the end.
Nice, thanks for sharing. Yeah, it looks very promising. It looks like, going back to the paper by Chamberlain, like this kind of thing, anytime you have a derived table or a derived database where you start off from a raw database and you're paring down the columns so that you have only a few select columns, and then perhaps you do a regression on it, and then regression allows you to predict predicted values at whatever your index points are, and that then makes another new table. It looks like, with this format, a good thing to have would be what they call provenance, and that was mentioned also in the presentation earlier, so that you can always see exactly what steps were used to go from table A to derive table B, so that you can always reverse, you can always go forward and backwards, you can transform table A to table B. And so like that kind of, like all the steps that you had input, let's say, I chose columns 10, 12, 13, all of those should be stored, saved, so that you can always have, you can follow the chain of commands up and down. I think that's one way to at least follow what was presented in one of these papers. But yeah, it looks cool.
Thank you.
Okay, any more questions or comments? Even though, would you mind opening your video for 1 minute before we close the meeting? Yeah, by the way, yeah, Brian, I don't think that you met Sunny Hall before, so maybe you could very briefly introduce yourself.
Introduce myself, or
I think Brian, you have not introduced yourself.
Oh, me
to
introduce
Sunny.
myself.
Yeah.
Oh, yeah.
Yeah.
Yeah, I'm a new faculty at the School of Earth Sciences at Zhejiang University, and my background, it's hard for me to describe in one word, but it's geophysics, geodesy, more recently glaciology, remote sensing, and machine learning, all of those things above. So I'm interested in, and also software engineering and data analysis. So that's why I wanted to participate in this meeting to see what's happening in the geochemistry space.
Okay, I think that's about it. Thanks, Luyan, for leading the paper, and thanks everyone for your participation. And let's meet the speaker on Wednesday. Have a good evening. Have a good day. Bye-bye.